So in this video, we're gonna start chapter number 11, which is alcohol, phenol, thiol, ether, and amine. And in this video or in this PowerPoint, we're gonna talk about the functional group that is present in the organic chemistry that we talk about, and then we have several functional groups that we're gonna talk about in this video or in this PowerPoint. So one of them is alcohol, second one is phenol, then thiol, ether, and then amine. And then we're going to talk about their physical property, how this functional group affect the physical as well as the chemical properties of the organic compound. So let's get started. So now let's get started with the introduction of the functional group. What is functional group in chemistry, how you define them. But before that, let's review our organic compound that we already talked about. So we know most of the organic compound are made up of carbon and hydrogen atom, right? But there are some of the organic compound that also contain some other atom beside carbon and hydrogen, and we call those atom as heteroatom. So organic compound can have oxygen, nitrogen, sulfur, or any other kind of atom beside hydrogen and carbon. So we name these kind of atoms as heteroatom. So make sure you know how you define a heteroatom. So now let's talk about the functional group. What is functional group? Functional group are the characteristic arrangement of an atom and the bond that function in a specific way in a chemical reaction. Or what you can say, you can also say a functional group is an atom or a group of atoms with characteristic chemical as well as physical properties, right? So functional group can contain an heteroatom, for example OH. This is one of the functional group, OH, that has an heteroatom, oxygen attached. It can have a multiple bond. If any organic compound has a multiple bond, let's say a double bond, so this double bond also be treated as a functional group. And sometimes the organic compound can have heteroatom as well as a double bond. So we're gonna talk about each of them separately. But what's the purpose of the functional group? A functional group determines a molecular shape. So that's why the functional group is so important, because functional group determine molecular shape. Second, it also determine the properties of the organic compound. Properties of the organic compound, as well as the third one is which type of reaction that organic compound can undergo. So all these properties or characteristic normally defined by the functional group, which kind of functional group you have in the organic compound. So we're gonna talk about multiple functional group in this chapter, but the only thing that we're gonna talk about, so those functional group always has a carbon single bond with a heteroatom that contain a functional group. For example, let's take an example. If you have carbon, how many bond carbon can make? 4. 1, 2, 3, 4. So this is your methane. This is an organic compound just containing carbon and hydrogen. But if I remove one of the hydrogen from this carbon, then carbon need one more bond to get stable. So instead of hydrogen, if I put oxygen, a heteroatom connected with the carbon through a single bond, so this make a functional group, right? So this is a characteristic arrangement of oxygen and hydrogen that is connected with the carbon with a single bond. So only this kind of functional group we're gonna talk about in this chapter, right? That has only single bond. So let's move on to the next slide and then talk about what are the different functional group that we have, and or what kind of functional group that we're going to talk about in this PowerPoint. So most of the functional group that we're going to talk about in this chapter are based or can be divided into two family or into two category. One of them is a hydrocarbon containing functional group. And the second one, we can say a compound that contain a single bond to a heteroatom. So we can have this example of hydrocarbon functional group on this slide, and then the single bond to a heteroatom. We can take an example like carbon attached to the 3-bond hydrogen, and then the 4th one attached to an heteroatom, right? So this heteroatom can be oxygen, can be nitrogen, can be sulfur, right? So functional group can be subdivided into these two categories. So on this slide we're going to talk about the hydrocarbon, and then later on we're going to talk about the single bond to a heteroatom, where carbon bind to a heteroatom through a single bond, right? So let's talk about the hydrocarbon functional group first. So we all know what is hydrocarbon. Hydrocarbon are those organic compounds that contain only carbon and hydrogen. For example, this, you have 4 carbon and then hydrogen, no heteroatom in there. So if you remember from the previous chapter, hydrocarbons can be of 4 types. One of them is alkane, right, where you have all the types of bond as single bond. Then we have alkene, second one. Then alkyne, we have a triple bond. Alkene, we have a double bond. And then the 4th one of hydrocarbon are aromatic, where you have a benzene ring, right? But for the alkane, we don't have any functional group in alkane. Why? Because alkane just do one type of chemical reaction, which is a combustion, and beside that alkane doesn't show any kind of, like, most probably no reaction. They are inert. So that's why we are not going to talk about any alkane or any functional group related to alkane, because it doesn't have any functional group. Then for alkene, we have a functional group which is a double bond, and because of the presence of the double bond we can have multiple chemical reaction, and all the organic compounds that contain a double bond can show a similar type of chemical reaction because of the presence of a functional group which is a double bond. Same thing apply for an alkyne. We have a triple bond as a functional group, and any organic compound or any hydrocarbon that has only a triple bond can show a similar type of chemical reaction. So you have to just look for the hydrocarbon. If you find a triple bond, then you can probably say, okay, with this particular compound, this triple bond will give you this product, because every compound that has a triple bond will give you a similar kind of product or similar physical properties. Then we have the 4th one, which is a benzene, which we call as aromatic hydrocarbon. So if any hydrocarbon that has an aromatic ring attached to it, so they might be showing a similar kind of physical as well as a chemical properties, because the base unit are same, which is an aromatic, right? So make sure you remember all these 3 types of functional group present in a hydrocarbon. Now let's try to take one example based on the concept that we just learned on the previous slide about the functional group on hydrocarbons. So this is the structure, which is a polystyrene, is a synthetic polymer made from styrene and used to make a hard plastic. Then what you need to do, this is a structure that is given, circle and identify the hydrocarbon functional group. So the main important term is here hydrocarbon functional group. And we know how many types of hydrocarbon functional group we have. We have alkene, double bond. We have alkyne with a triple bond, and we have an aromatic ring, which is a benzene ring, right? So if you remember, benzene ring can be shown with a circle at the center of the hexagon, or you can just put a double single bond, right? This is also a benzene. So let's try to solve this problem over here. So if you see, this is a structure. We know we have this structure. This structure is an aromatic ring. So this is one of the functional group. Then we can see we have a double bond. So this is, we have alkene as a functional group. And then we can see we have a single bond over here, but we know single bond cannot act as a functional group because that looks like or has no chemical properties. So we have just 2 functional group in there. One of them is aromatic ring. Second one is an alkene. So from this type of structure, you can easily figure it out which type of hydrocarbon functional group you have. Let's take an example. So if I give you this structure and I ask you how many types of hydrocarbon functional group that you have in this structure, so the time you see over here, is this a aromatic ring? No, this is just a alkane, which is a cycloalkane, and we all know if there is an only single bond, there is no functional group in there. This is not an aromatic ring. So make sure you will be able to easily differentiate between aromatic ring or just a cyclo compound, right? So this is not any hydrocarbon functional group. What about this one? The time I see this is a double bond, so I know this is a double bond functional group, which is alkene. And which kind of functional group is this one? This is a triple bond, which is alkyne. So we have two types of functional group hydrocarbon, alkene and alkyne. So this is how you normally can differentiate and figure it out how many types of you have it, right? Now let's try to learn about drawing a skeleton line structure as well as the condensed notation for a molecule that contain a carbon single bond heteroatom. So we're gonna learn if you have any loose structure, which is the given loose structure that has some heteroatom present in the structure, how you can draw a skeleton line structure as well as the condensed structure, right? So let's start with an example over here. This is a loose structure given for any compound, and if in this compound, if you can see, you have 1 2 3 4 carbon, and then between 2 and 3 you have one heteroatom over here, heteroatoms, right? So this is a loose structure which we also call as expanded structure, because we are expanding the structure and then we are showing each and every bond that we have in the given molecule. And now how are we gonna write that skeleton line structure? And what's the other name for this skeleton line structure? Line angle formula. So you can say line angle formula and a skeleton line structure that we already learned in the previous chapter too. So how you're gonna do a line angle formula? We have to show line, but for this particular structure we have 4 carbon and between 2 and 3 we have an oxygen, so we just do 1 2, then you have an oxygen, and then you have this. So this is 1, this is 2, this is 3, this is 4 carbon, and you have to show a non-bonding electron on the heteroatom, which is oxygen in there. But if you can show it, that's good, but sometimes the non-bonding electron, which is this, and if you remember what is non-bonding electrons, so those electrons that doesn't participate in the bonding in the compound. So we usually don't show the non-bonding electron in a line angle formula or a skeleton line structure. But what you need to do, you have to show a heteroatom in a line angle formula or a skeleton line structure. You cannot remove the heteroatom whenever you're drawing a skeleton line structure. You cannot draw the structure something like this, 1 2 3 4, even though this compound also has 4 carbon like we have over here, but you have to show the oxygen too, and we don't have any oxygen in here, so this is not the right skeleton line structure for this. So remember, always show a heteroatom in a line angle formula. We just don't show a carbon and a hydrogen, but you have to specify or show up any heteroatom. The second important thing that you need to know while drawing a skeleton line structure for any organic compound that contain a heteroatom, that you have to show a hydrogen atom, all the hydrogen atom that is connected with the heteroatom. We just don't show a hydrogen that connected with the carbon, right, in a skeleton line structure. But if any hydrogen attached to any heteroatom, you have to show. If you don't show it, then that's a wrong structure. For example, the structure that is given over here, how many carbon you have? 1, 2, 3, and on the second carbon you have a heteroatom attached instead of a hydrogen, right? You put a heteroatom oxygen, and then on that oxygen you have a hydrogen. So if you have to draw a skeleton line structure, you have to show a line angle formula or skeleton line for all the 3 carbon, which is 1, 2, 3. But on the second carbon you have an oxygen, and like we said, we have to show a heteroatom, which that's why we drew the structure oxygen. Then we also have to show a hydrogen attached to that oxygen. And if you can see over here on these carbon, we usually don't show hydrogen. That's what we learned. But for heteroatom you have to show, right? So this is the right structure, and this is also a right structure. So if you don't have to show a bond between oxygen and hydrogen, you just write OH as a condensed structure, right? So make sure you know this thing. If you don't draw it, let's say if I draw the structure, same structure, something like this, O, and if I don't show a hydrogen, then what's wrong with this structure? So if I don't show, and if we don't write the hydrogen over here, that means we have a carbon in here. If you remember from the skeleton line structure, if you have something like this, so that means we have some carbon ending, and which is not true. That's why you have to show a hydrogen. So keep this in mind, because if you don't write it, the entire structure might be a different structure that you wanted to draw. Okay, so now let's go to the next slide and try to solve a couple of problems based on the concept that we just learned about how to draw the skeleton line structure of any organic compound that contain an heteroatom. So the problem says to write the skeleton line structure for the following Lewis structure. So these are the Lewis structure. Then you have to draw a line angle formula of the skeleton line structure. So how many carbon we have on here? Over here 1, 2, 3, 4, and between 3 and 4 we have an oxygen. So let's make the line angle formula or the skeleton line structure. 1, 2, 3, then 4th, and between 3 and 4 we have a heteroatom, right? And then we have some non-bonding electron pair. If you don't want to show a non-bonding electron pair, you can draw the same structure, something like this, and that's it. So in this structure I'm not showing any lone pair or a non-bonding electron pair. So this is also correct, this is also correct. Let's go to the second one. How many carbon we have over here? 1, 2, 3. So 1, 2, 3. Then on the third carbon we have a single bond attached with an heteroatom, and that heteroatom attached with the hydrogen. So we have to show this hydrogen too. So that's why we have an hydrogen over here. And you can draw the same structure, something like this, OH, without showing a non-bonding electron pair. So both the structure are right. Let's do a couple of more. So this is also a Lewis structure. This is also a Lewis structure. And if I have to draw the skeleton line structure, how you gonna draw it? So how many carbon you have in this entire organic compound? 1, 2, 3, 4, 5. So you have to draw 5. 1, 2, 3, 4, 5, and between 3 and 4 you have a nitrogen. So you have to show a nitrogen, and on that nitrogen you have hydrogen. You have to show the hydrogen. If you don't want to show a bond between nitrogen and hydrogen, that's okay. So I can draw the same structure, something like this. Let me draw it. 1, 2, 3, nitrogen, 4, 5, and you can just write H if you don't want to show this bond, right? So we have 1, 2, 3, 4, 5, and we have nitrogen, hydrogen, but I still have to show the hydrogen attached with the heteroatom, right? And then if you see, I also didn't show the lone pair or the non-bonding electron pair, so it's also okay. Let's go for the D. How many carbon? 1, 2, 3, 4, and then on the second we have one more, right? So I can draw the line angle structure. 1, 2, 3, 4. We have one more on the top, which is as a substituent, and then we have sulfur attached to this carbon, single bondly, and then that sulfur also has a hydrogen. And if you can see, we have a 2 lone pair or 2 non-bonding electron pair on the sulfur. So I can draw exactly the same line, skeleton line structure, and on the sulfur we have to show the hydrogen too. We cannot remove it, right? So if you can see sulfur hydrogen with two lone pair, if you don't want to show it, you can just draw the same structure like this, SH, right? So this is 1 2 3 4, this is 5, and you have this group, sulfur and hydrogen. So this is how you normally draw a skeleton line structure for any heteroatom containing organic compound, right? So now let's start with the another type of functional group beside the hydrocarbon functional group that we learned. So the next one is alcohol functional group. So alcohol are a class of compound that contain a OH group, which we call as a hydroxyl group. So if alcohol can be treated as OH group, that is single bonded to any carbon, so this is your alcoholic group or a hydroxyl group, right? So let's take an example. If you have this 4 hydrogen attached with the carbon, right, and if I remove the fourth carbon, a fourth hydrogen, and replace with an OH, so this is your hydroxyl group, right, that is connected to a tetrahedrally structure or tetrahedral carbon structure, right? And then sometime we usually write an alcohol group like ROH. What is this R? R is a carbon containing organic compound. Carbon containing organic compounds. So this RB can have 2 carbon, 3 carbon, 50 carbon, 100 carbon. It just show you we have any carbon, right? So let's take an example on the next slide, and then we'll just talk about more about this ROH. So we just learned on the previous slide, then the functional group alcohol has, we can write as ROH, right? So this OH is your hydroxyl group, functional group, hydroxyl group, and this R is a carbon containing, is normally to show you the carbon, how many carbon we have in that organic compound that has an OH group attached to it. So for example, we can have CS3 OH, we can have CS3 CS2 OH, or we can have CS3 CS2 CS2 OH. So this group remain the same, but what's happening over here, the number of carbon is increasing, right? You have 1 carbon, you have 2 carbon, you have 3 carbon. So the properties of all these 3 organic compound with a functional group of OH or any functional group does not depend on these carbons. So the property or the chemical reactivity of the functional group doesn't depend on these carbon, and we usually show these carbon in the form of R, because the property, like I said, doesn't depend on this R, right? If the OH is present as a functional group, it will show its chemical or physical property. Doesn't matter how many carbon is attached to that functional group, right? So we can write this as ROH. So this R can be any hydrocarbon that contain carbon and hydrogen, right? So with what it can be a single bond, it can be alkane, it can be alkene, it can be alkyne, or it can be an aromatic compound, right? So this R can be any of these hydrocarbon that we just learned. So with alkane can be a cycloalkane too, right? So let's take an example. if I draw something like this, OH, this is an R and this is OH. What is this R in there? This is a 3 carbon containing alkane that has carbon and hydrogen attached with an OH as a functional group. And if we talk about an alkene, I can draw the same structure, but I can put a double bond in here. So this is also treated as R that has an alkene in there. If I talk about an alkyne, we can have a triple bond as an alkyne too, right? Or we can have a cycloalkane. For example, if I have something like this, what's this name? This is cyclopentane. We already learned about how to name any cycloalkane. And if I remove one of the hydrogen and replace with OH as a functional group, so this can be treated as an R that contain carbon and hydrogen. So basically R can be of any of the hydrocarbon and then that attach with any of the functional group. So this is the main concept that you need to learn from this example or this thing that we just learned over here. And one last thing, if you can see, we have different R group. We can have single bond alkane, we have double bond alkene, we have triple bond alkyne, we have cycloalkane. So does it depend? So is gonna change the chemical and physical property of this functional group? No. So that's why we usually don't write these big carbon containing hydrocarbon, carbon and hydrogen containing hydrocarbon with the functional group. That's the main reason. So there are some more example of a compound that has an alcohol as a functional group. So we have CH3OH, we have carbon with a 3 hydrogen. I can say ROH, or if you want to write the exact structure, that's your CS3OH, you have 1 carbon. If you have the another structure 1 2 2 carbon, so you can write CS3 CH2, then you have to show the OH, the functional group. Right. Similarly, the last structure CH3 is over here, then you have carbon that has also CS3 attached to it over here, and then the same carbon has OH group, so we just write OH, the condensed structure. And we can also form a skeleton line structure for CS3 CH2. You have 1 2, this is OH, you have 1 2 3, on the second carbon we have OH group attached. Right, if you can see over here, this is 1, this is 2, this is 3. On the second carbon we have OH attached. That's why we have this structure. Right, so this is how you normally draw all kind of structure. And we already talk about writing the correct alcoholic structure that must include oxygen and its hydrogen. So it can be written as O bond H or just OH. We already talk about this thing, right? So that's why we have different alcoholic group in here. So now let's try to do some problem based on the concept we just learned about the alcohol functional group. The problem says write the skeleton line structure and a condensed formula for the following alcohol. How would I know these are alcohol compound? The time I see OH, I know this is a hydroxyl functional group, this is alcohol, right? So how to draw the skeleton line structure? You have to just count 1 2 3 4 5. So basically this entire carbon and hydrogen containing region we call as R, right? So that's why we have ROH, right? But we have to show the skeleton. So how many carbon? We have 5. So that's why we have to make 5 carbon, 1 2 3 4 5, and on the 5th carbon you have OH group attached. You have the 5th. If you don't want to show the non-bonding electron, you can just draw the same structure like this, OH, that's it, right? So this is how you normally draw the skeletal line structure. But if you have to write the condensed structure, you can write something like this. So on the first carbon you have 3 hydrogen, so CH3. On the second you have CH2. And how many CH2 you have? We have on the second CH2, third you have 2 hydrogen, on the third you have 2 hydrogen. So I can say CH2 is 3 times, and then on the 5th one you have 2 hydrogen attached, and then on the 3rd bond, 4th bond, you have OH. That's your condensed structure. Same thing happening for the B part. So you have 1 2 3 4 5, you have 5 carbon, just draw 1 2 3 4 5, then show on the 3rd one you have a hydroxyl group attached with a non-bonding electron pair. If you don't want to show it, just remove it and just write OH. And this is a condensed structure formula. 1 2 3 4 carbon, 5 on the 3rd you have OH. Right. So we only learn about how to draw the condensed structure, skeleton line structure. So make sure you practice couple of time, and then make sure you know how to draw all these type of structure for an functional group. In this case we are talking about the alcoholic functional group. Now let's get to the naming part of the alcohol, right? How you name an alcohol. So there are a couple of rules. We already learned on the previous chapter how to name any hydrocarbon, right? So the same rule will apply over here, but the only thing is only thing on this alcohol part is whenever you write the parent name, the last part E, which is an alkane, replace with OL, and this OL will tell you we are talking about alcohols, right? So let's go to the next slide and talk about some more rule, but this is basically the same rule that if you already know how to name an alkane, alkene and alkyne, there is just a little bit twitch in there. Then we're gonna do some problem on some example that will help you to understand more about the naming, but the rule almost is the same. So the third rule says number the parent chain starting from the end closer to the hydroxyl group. So we have to give the preference or the priority to the OH group, alcoholic group, so that it can get the lowest number possible. If you remember from the previous slide or previous chapter, we always give the preference to a double bond, triple bond, if there is any, right, in hydrocarbons. Same thing, same rule apply over here. If you have an OH group, you have to give the preference to the OH group so that it can get the lowest number in the parent chain. And then the last one, place a locator number and hyphen before you name your entire molecule. So let's get to the next slide, and then let's do some problem and try to understand how to name it. So let's try to do this example over here. So you have this structure which is given, and we have to write the name of this structure. So the time I see OH, I know this belongs to the alcoholic functional group, and we have to name according to an alcohol, not an alkane, not an alkyne, just according to the alcohol. So what's the first rule says? So first rule says you have to figure out the parent chain, the longest chain, right? And then if there is any functional group is present, you have to give the priority to the functional group. You have to give the lowest possible number. So the numbers start from the right, 1 2 3 4 5 6. So in this case the second carbon has the functional group OH. Can I start it from the other side, something like this over here, 1 2 3 4 5 6? Is it possible? No, because if we start counting from this side, then the carbon that has the OH group getting the 5th number, which is the highest number, right? Which is not possible. We have to give the lowest possible number, so which is 2. So we have to start from right to left. This is the correct way of writing, not counting, not this one. So again, so we have 6 carbon. What's the 6 carbon containing organic compound? Hexane. And then because this is an alcohol, we have to specify in the name too. So we remove this E, and instead of E we write OL. So the name is hexanol. So we always remove the E, last E, and then replace with OL, right? So we know this is an hexanol. The time I read hexanol, I know this hexane 6 carbon compound has an hydroxyl group, OH group, but where does it present? I don't know. So we have to specify the location of the hydroxyl group. So on the second carbon, we have the hydroxyl group present, so we have to indicate the number, right? So the name is 2-hexanol, and if you remember, is exactly the same that we did for alkene and alkyne. We have to specify the location for alkene and alkyne. Same thing we have to do for alcoholic group. We have to specify the location. If we don't write the location, that means we are assuming this is on the first carbon in the compound, but in this case this is not the case, so that's why this is 2-hexanol. Let's do one more problem, how to name this structure. So the first rule, you have to figure out the parent chain, the longest possible chain, and in that possible longest chain you have to include a carbon that has the OH group attached. You cannot miss that carbon in the parent chain. So let's get started. So in this example, start from here, 1 2 3 4. Then I have a chance to go up to get it 5. Is it possible to go 5? No. The time I see we have 2 more carbon straight, I don't want to go up because we left with just 5 carbon, or well, and we know we have a chance to go to the 6 carbon, the maximum number of carbon. So we are not going up, we are going straight 5 6, and this carbon act as a substituent now, right? So this is one way of writing. So in this case the second carbon is getting the hydroxyl group, right? Can we start from the other way around? Can I say this is 1, this is 2, this is 3? I don't want to go up because this is just 1 carbon. Even if I see that we have 3 more carbon straight, then we have to go straight 4 5 6. Is it possible to count like this? You can, but the problem is over here is the carbon that has the OH group is having the 5th number, and we already talk about we have to give the lowest possible number to the carbon that has an OH. So this is not the correct way of writing, right? So this way is the correct way of writing or counting the number. So now let's see how you can name it. So how many carbon total in the parent chain? 6 again. So 6 is what? Hexane. But instead of writing hexane, I am just removing E and then writing OL, the ending word for an alcohol containing compound. So hexanol. And now we have to see what kind of functional group that we have. So first we have to write on the 4th carbon we have a substituent. What's the name of the substituent? We have 1 carbon. This is methyl. So I can write on the 4th carbon I have a methyl group, and then we can write 4-methyl hexanol. We can write, but we are still missing some important information over here. The time I say hexanol, I know we have an alcoholic group present in this organic compound, but where? If I don't write it, so we are assuming is on the 1st carbon. Is it the case in this compound? No. The OH group is present on the 2nd carbon. So you have to specify the location too for OL. So it's 4-methyl-2-hexanol. Sometime you can also write 4-methyl hexane, then you can write 2-ol. So this represent on the 2nd carbon you have OL group too, right? So there both ways of writing the name is right. 4-methyl-2-hexanol or 4-methyl hexane 2-ol. Right. So this is how you normally write the name of any alcohol. So till now we just learned about how to name any organic compound where the structures are given, but let's try to do a problem where the names are given and you have to draw the structure. So we are going in opposite way, right? So the problem saying provide a skeletal line structure for these alcohol. So let's try to learn how we got these structure from the naming. Right? So let's start with the first one. The time we say this is octanol, what is octane? Octane is a 8 carbon compound, right? So let's say how many carbon we have? 1 2 3 4 5 6 7 8. So just draw 8 carbon. and the time I see OL, I know this compound also contain an hydroxyl group. But where? This is the location. On the third carbon we have a hydroxyl group, so just put on the third carbon OH group. So this is how you draw 3-octanol. Right. Let's do about the B, cyclopentanol. The time I say cyclopentane, just remove the alcohol right now. If I say cyclopentane, what is cyclopentane? Cyclopentane is a 5-carbon ring of single bonded, right? And the time I see OL, this is alcohol, so I can put OH on any of the carbon of this cyclopentane because each and every carbon are similar, right? If I put something like this on the top, this is also cyclopentanol because each one of the carbon that making a cyclopentane have the same or similar location. You cannot differentiate which one is one, which one is second. Then we have the third one, 5,6 dimethyl 1-heptanol. So how you gonna draw this structure? You have to just look first the parent chain. Heptane is a 7-carbon containing ring. 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. And then the time I see OL, I know this compound has an alcoholic group. Where? This is the location on the first carbon. So you have a choice, either you can put OH over here on the first carbon or you can put over here. But wherever you are putting the OH group, you have to treat that carbon as a number 1 carbon. Good. So I'm putting OH on that carbon, right? So this is our first carbon. Then this is 2, this is 3, this is 4, 5, 6, 7. So we already done with this 1-heptanol. Now we left with 5,6 dimethyl. So we have, what is dimethyl? You have 2 methyl group, and what are the location? One on the 5th group, 5th carbon, one on the 6th carbon. So your 5th. So this is your one methyl group, and on the 6th one you have this, right? So this is the structure of 5,6 dimethyl hexanol or 1-heptanol, 7 carbon. So the only the thing that you need to know, even though in this structure we have some substituent, but still we have to start with an carbon that has a OH group, because OH will get a priority over the substituent whenever you start counting the number. So remember this thing, OH will always get a priority wherever you have to just figure it out which end you have to start counting, right? Even though there are multiple substituents attached, you have to start with the carbon that has OH, right? So let's take a couple of more example on the naming of alcohol and try to learn or practice some more. So if I give you this structure, this is chlorine, this is OH, how you name this structure. Then we have another structure, this is OH, this is one of the substituent, right? So let's try to name these two structure. How you name this one? So the time I see OH, I know I have to give the lowest number to the carbon that has OH, so this is the 1. Even though we have a substituent which is chlorine, we don't care about this thing. We have, our priority will be the carbon that has an OH. So this is 1 2 3 4 5. So this is how you start counting. We cannot start from this side. If we would have started from this side, the carbon that has OH will get the 5th number, which is not possible. So how you name it? So first we have to write the substituent. On the 3rd carbon I have chlorine. Chlorine is chloro. We already learned about this thing. Then we have how many carbon? 1 2 3 4 5. 5 is your pentane. And then instead of write pentane, I end with pentanol. So do I have to specify where the OH group is? It's up to you. If you don't specify, I know then is should be belong to the first carbon, which is the case. If not, you can write the same name like this: 3-chloro 1-pentanol, or you can also write 3-chloro pentane 1-ol. So this one indicate where you have the hydroxyl group. How you name this compound? So you have a cyclo compound, right? So how many carbon you have in cyclo? This is cyclopentane, right? And then you have OH group. The time I see OH, I know the carbon that has the OH group attached, we have to specify that carbon as 1, the priority. Then we have to start counting backward or counterclockwise: 1, 2, 3, 4, 5, right? So because after the carbon that has the functional group, we have to give the priority to the second substituent, which is in this case, and what's the name? Methyl group. So we can write 3-methyl, and then what's the name? We have to write cyclopentane, and then on the first carbon we have ol, pentanol. So like I said, in a cyclo compound you don't normally show or write 1, because if you don't write anything, that means the hydroxyl group on the first carbon. Or if you want, you can write 3-methyl 1-cyclopentanol, or you can also write 3-methyl cyclopentanol pentane. Let's do pentane 1-ol, right? So each of the way is right, but this is how you normally write for any compound that has a substituent or any cyclopentane containing compound, right? So make sure you practice naming of these kind of compound. So now let's talk about the types of alcohol. So we'll see the chemical reactivity or chemical property of an alcohol also depend on the number of other carbon atom attached to the carbon atom that has an OH group. So for example, if you have this CH3 CH2 and this is OH, so you have this alcoholic group over here and this alcoholic group attached to this carbon, and we're gonna see how many carbon attached to this carbon. So if you can see, this carbon attached to just one carbon, right? So this type of alcohol we call as a primary alcohol, because the carbon that has an OH group attached to only one of the carbon. But if you remove one of the hydrogen from here and replace with one more carbon, CH3, so now the same carbon attached to how many more carbon? 1, 2. Now this becomes secondary alcohol. And if I remove the third hydrogen over here and replace with one more CH3, so this means this carbon that has attached to OH attached to how many more carbon? It attached to this carbon, second, third. So that makes it a tertiary alcohol. So depending on how many carbon attached to that carbon that has an OH, you can specify the type of alcohol, whether it's a primary, secondary, or a tertiary. So let's take an example on the next slide so you will understand better. So this is another example, right? So let's say this is a carbon that is attached to a hydroxyl group, and this carbon attached to how many carbon? This attached to just one more carbon, because if you remember, even though this written as R, what is R? R is a way of writing multiple carbon, right? This R can have 2 carbon, 3 carbon, 4. It doesn't matter, because this carbon only attached with one more single carbon, right? So for example, this carbon can be CH2, CH3, right? So we don't care how many carbon you have after this. This carbon is attached only with this carbon, just one more carbon. So that's why this is a primary alcohol, or 1R group you can say. If the same carbon that has the OH group attached with 2R group, or means 2 carbons, that means this is a secondary alcohol. And the same carbon attached with a 3R group or 3 carbons, that means there is a tertiary alcohol, right? So make sure you know this concept. Let's try to do some example and let's try to figure it out which kind of carbon or which kind of alcohol you have in that particular compound. So the problem says indicate whether each of the alcohol shown below is a primary, secondary or tertiary alcohol. So let's take this example over here where we have alcohol. We have this is your alcohol part and the carbon is over here. So we have to see this carbon attached to how many carbon? This carbon attached to this carbon, this carbon attached to this carbon. So this carbon attached to 2 more carbon. So this is why this is a secondary alcohol. What about the B part? This is the carbon that attached to the OH group and this carbon attached to just 1 more carbon, right? So that means just primary alcohol. What about this one? This is the carbon that attached with the OH group and this carbon attached to this carbon and this carbon, means 2 carbon. So this is secondary alcohol. And then the last one, this is the carbon that attached with the OH group and this carbon attached to 3 more carbon, right? Carbon, carbon, carbon. This is carbon. So 1, 2, 3. So tertiary alcohol. So this is how you normally differentiate which type of alcohol you have in that particular compound, right? If I give you this example, OH, and if I give you something like this triangle, and then you have this OH and you have one more. So let's figure it out which type of alcohol is this one. So this is the carbon that has the OH group attached and this carbon attached to this carbon and this carbon. So secondary alcohol. What about this carbon? This is the carbon that has OH group. This carbon attached to this carbon through this bond. This carbon also attached with this carbon through this bond. And this carbon also attached with this carbon through this bond. So that means this alcohol is a tertiary alcohol. So this is how you can determine. So make sure you practice couple of times to determine which type of alcohol you have. Now let's talk about the different kind of alcohol which we name as diol, triol and polyols. As the name is saying, if any organic compound has 2 alcoholic or 2 hydroxyl group attached, we call as a diol. Tri means 3. If you have 3 hydroxyl group in a compound, we call as triols. And then we have poly. Poly means if you have more than 3 alcohol present in a compound or in any organic compound, we call as polyols. So let's take an example. This is the organic compound. How many hydroxyl group? 2. Ethylene glycol is a diol. Then we have propylene glycol. How many hydroxyl group? 2. Diol. Then we have a glycerol. How many hydroxyl group? 3. Triol. Right, and we can also show the same structure like this. Where 2, right? 3 triols. Then we have one more example of glucose, which is a polyol. So this is the structure of glucose. How many alcoholic group we have? We have 1, 2, 3, 4, 5. Right, so in this structure we have 5 hydroxyl groups. So if this is more than 3, so that means glucose is a polyol, multiple alcohol. Right, so this is how you can differentiate between the different compound, whether it's a diol, triol, polyol. Right. So let's take one problem on this. The structure of latanoprost, a treatment for glaucoma, is shown below. So this is the structure and you have to answer these A, B, C. Circle and identify the alcoholic functional group. So we have this 1, 2, 3. Label the hydroxyl group as a primary, secondary and tertiary. So let's figure it out. Which type of alcohol is this one? So let's talk about the first, this one. So this is the carbon and this has the OH group and this carbon attached to 2 more carbon. So this is a secondary alcohol. What about this one? This carbon attached to this carbon and this carbon, secondary alcohol. This carbon that has the OH group attached to this carbon and this carbon, secondary alcohol. So all the three alcoholic group or hydroxyl group attached to a carbon that attached to two more carbons. So this is a secondary alcohol. And whether this structure is a diol, triol or polyol, triol, because we have just three hydroxyl group in there. That's why it's a triol. So this is how you normally solve this kind of problem. So now let's talk about some of the physical properties of any organic compound that has an alcoholic as a functional group. So the first of the physical property that we're going to talk about is the solubility of the alcohol. So what do you think, whether the alcohol is soluble or not? So if you have this structure OH, so what we have on this side, this is your hydrocarbon part, means it has just carbon and hydrogen, and we know carbon and hydrogens are non-polar, so they cannot dissolve in water, right? So solubility is nothing, but because of the presence of this functional group, alcohol functional group, what do you think? This OH group makes this hydrocarbon a little bit soluble in water? Yes. Why? Because the OH group is a polar bond containing group, right? And because of this polarity, this will get partial negative, this will get partial positive, and because of these charges, this can interact with water, right? Water is also a polar molecule, and because of the polar dissolvement polar, then most of the alcoholic containing compound are soluble in water. But there is a condition: you cannot have more carbon attached to the OH. So for example, if I have something like this structure and you have one OH group at that, even though the OH group is a polar, it can interact with water, but the majority part of this structure are non-polar. So only one single hydroxyl group, even though it's polar, cannot help to dissolve all the carbon that we have attached with this compound, right? So there is a limitation, and then we're going to talk about on the next slide how many carbon, or what's the ratio between hydroxyl group and carbon, how many carbon can be dissolved by each hydroxyl group, right? So let's go to the next slide. So this is the way we normally see whether the alcoholic molecule is soluble in water. So if you can see, if you have one carbon, two carbon or three carbon, those compounds are soluble in water, right? What's the name of this compound? You have one carbon, you have alcohol, one is methane, methanol. So methanol is soluble in water. What's the name of this compound? You have one, two, then two is ethane, and this is alcohol, ethanol, right? I'm not specifying the location because we are assuming this is on the first carbon, so I counted it wrong. So this should be 1 because we have to give the priority to the OH. This is 2, then again 1, 2, 3, this is propanol. So what you see over here, if you have 3 carbon attached to only one hydroxyl group, they are soluble, right? Then we have some partial soluble in water. If you have more than 3 carbon attached to just one hydroxyl group, then hydroxyl group is still finding it difficult to dissolve the entire carbon in water, so they are partially soluble. But once it crosses the 4 carbon, 1, 2, 3, 4, 5, then it becomes insoluble even though you have hydroxyl present. Then the entire compound is insoluble because you have too many non-polar carbon containing compound that has a carbon in there, right? So just remember the ratio is 1:3. So if you have 3 carbon and 1 hydroxyl group, then it can become soluble, but after that it becomes difficult to get soluble in water for all the carbon that has a hydroxyl group. So let's take an example of alcoholic solubility one more time. So glucose, as the structure is saying over here, you have 6 carbon and you have 6 hydroxyl group in a glucose molecule. So that's why glucose is a water soluble, even though it has a 6 carbon. But to dissolve 6 carbon, how many alcoholic group you have in the same structure? 6 OH. So the ratio is 1:1. So each hydroxyl group needs 1 carbon to get dissolved. So that's why glucose, even though I have 6 carbon, is easily dissolved in water. Compared to the cholesterol, if you see, cholesterol has just 1 hydroxyl group and you have too many carbon containing compound, which is a non-polar part, and 1 hydroxyl group cannot help to dissolve all these carbon containing group that we have. So that's why cholesterol is insoluble in water, right? So this is how you can determine whether the given compound of alcohol is a soluble in water or a non-soluble in water. So now let's talk about the second physical property, which is a boiling point. And the boiling point depends upon the interaction, which kind of force of interaction, intermolecular force of attraction that we have within the molecule. So if that molecule has a hydrogen bond, that means this is the strongest kind of intermolecular forces. So that means the boiling point of that solution is higher compared to the one that has just dispersion forces. So we're gonna see that alcohol can make a hydrogen bond with another alcohol in a solution. So we'll see how. So this is one of the alcoholic molecule, which we call as methanol. We have another molecule, methanol, and if you can see this OH bond, which are polar, so this will get a negative charge, oxygen positive charge. Same thing for any other molecule that of methanol which is close by. Hydrogen will get a positive, oxygen will get a negative, and oxygen and hydrogen from each, between two atoms, two molecules of methanol can show a hydrogen bond. So this is your hydrogen bond. And if you remember that, what's the requirement to make a hydrogen bond? So requirement is if the hydrogen attach with nitrogen or oxygen or fluorine, and you have any of these atoms side by side, they can make hydrogen bond. So we already know this oxygen attached with the hydrogen, this oxygen attached with the hydrogen, and this hydrogen can make a hydrogen bond with this oxygen from any other molecule, so they can make a hydrogen bond, right? Same thing if you have the third molecule of methanol, same hydrogen from the one of the alcoholic molecule make a hydrogen bond with the second oxygen from the second molecule, right? And because of these hydrogen bond present, alcohol has higher boiling point compared to their counterpart. So for example, if I say between the two structure, which one has a higher boiling point? So this is just an simple alkane, this is just propane, and what's the name of this? 1 2 3, this is propanol, alcoholic group. So even though they have the same carbon atom on both sides, but because of the presence of alcoholic group in propanol, propanol has higher boiling point because they can make a hydrogen bond. Instead of propane, propane doesn't have any polar compound or polar bond, so it cannot make any hydrogen bond. It can just show dispersion forces, which is very weak. So that's why propane has lower boiling point compared to an propanol, right? So yeah, so this is how you can compare methanol and ethanol and 2-propanol liquid at room temperature, where alkane of similar size are gases because they don't have enough intermolecular forces, so they behave as a gas. Let's take one more example. So you have one alkane, 1 2 3 4 5 6. You have one of the compound called hexane, and then the second one we have is 1 2 3 4 5, so we can say is pentanol. So out of the two compound, which one has a higher boiling point? The time I see alcoholic group, I know they can make a hydrogen bond with themselves. whereas it cannot form any hydrogen bond, the hexane. So that's why pentanol will have a higher boiling point compared to the hexane, right? What kind of force hexane has? Only the dispersion forces, the non-polar bond or molecule have, right? So this is how you normally differentiate which one has a higher boiling point, which one doesn't have it. So we are done with an alcohol. So now we're gonna start with another functional group which we call as a phenol, right? And we're gonna talk about what is phenol, and later on try to learn how to name any organic compound that contain a phenol. So let's get start. What is phenol? Phenol is an aromatic ring with an hydroxyl group attached as a substituent. For example, so this is your benzene ring. If I remove one of the hydrogen on any of the carbon that is in the benzene, so let's say this is the hydrogen. What's the formula for benzene? C6H6. For each carbon you have one hydrogen. So if I take out one of the hydrogen from any one of the carbon, let me take out this hydrogen, and if I remove OH instead of hydrogen, if I attach, then this entire thing become a phenol. This is not a benzene anymore, or you can say benzene attached with an alcoholic group we call as a phenol, right? So phenol group, because of the presence of the phenol group or the OH group attached to the benzene, they act as a different functional group than alcohol or aromatic hydrocarbon. So whatever the chemical and physical property this phenol is going to show is going to be different than just benzene or just any kind of alcohol, right? So we're gonna learn about what kind of property they're gonna show, right? And we can show in different way. You can show like this with a double single bond, or you can show a phenol with a 6 carbon member ring with a circle at the center. This is also a phenol, right, with an OH group attached. So yeah, so let's go to the next slide and try to name how to name any compound that contain a phenol. So the naming of the phenol is exactly the same thing that we already learned about how to name an hydrocarbon and alcohol. The only difference is over here the parent chain will be a phenol. So let's take an example over here. If you see this structure, this is a benzene, and the time I see this benzene attached with an OH, then this entire thing become as a phenol, and we can use this as a parent chain, right? And then anything attached to this parent chain we can act as a substituent, right? So let's see. So this thing that is attached to the phenol act as a substituent. Then how you name it, you have to just specify the number on the substituent. You have to give the priority to the carbon that attached with an OH. So 1, then you have to give the second lowest number to the substituent, then 1 2 3 4 5 6. On the third carbon you have an ethyl group as a substituent, and what's the parent chain? Phenol. So the name is 3-ethyl phenol, right? Not 5-ethyl phenol, because you have to go clockwise, right? Not on this way. This is incorrect. So now let's try to draw some skeleton structure of the following compound. The time I see methyl benzene, then if I see benzene, I know what is benzene is. Benzene is a 6-member ring structure with alternate single double bond, and the time it says methyl, so methyl is a substituent, so I can put a methyl group anywhere on this 6 carbon. So the structure show over here is they put it the methyl group something like this. I can do, this is also benzene, I can do something like this. This is methyl benzene. I can make this way methyl benzene, right? So this is how you normally draw from the name. The part B says 2-methyl phenol. The time I see this name, I know this is a parent chain phenol. And what is phenol? Phenol is a benzene with an alcohol group. That's your phenol. And then it says on the second carbon of this phenol you have a methyl group, so you have to specify this is your 1, this is 2. You can just write methyl group. This is your 2-methyl phenol. Same thing like this, same thing, right? So this is how you normally draw the structure, by looking at the name of the parent chain, right? So let's take a couple of examples on the phenol that we just learned how to name it. So if I give you this structure, what's the name of this structure? We have 2 chlorine and then we have OH on this benzene ring. Then we can have so let's try to name these 2 compounds that has a phenol group. So let's start with the first one. The time I see this is a benzene ring, and the time I see this attached with the OH, I know this entire thing is your phenol group, right? So I know the parent name has to be phenol. And then now you have 2 substituents and both of them are chlorine, so you have to start naming or numbering the system with the carbon that has an alcohol group attached to it. Now you have a choice, either you can go clockwise or anti-clockwise. So which way you have to go? So you have to go downward, clockwise, because the time I see 2, the first substituent occurring on the second. If I would have gone counterclockwise, then the first substituent would have occurred on the third one. So we have to go to the clockwise, because we have to give the lowest number after the carbon that has OH group, right? So 1 2 3 4, this is 5, this is 6. So I can say 2 comma 5, how many chlorine? Dichloro phenol. So on the phenol, on the second and fifth carbon, we have 2 chlorine atom attached. What about this one? The time I see this is structure benzene plus alcohol, this is phenol. So I know the parent name will be phenol. Now you have to specify the numbering, so you have to give the priority to the carbon that has OH group attached, 1. Then it doesn't matter whether you go clockwise or anti-clockwise, in both cases you will get the other substituent on the second carbon. So let's go 2 3 4 5 6. If I would have gone the opposite way, like 1 2 3 4 5 6, it doesn't matter, because all the substituents will get exactly the same numbering. So it doesn't matter in this particular case which way you start counting, right? So what should be the name? So I can say 2 comma 4 comma 6 trimethyl phenol, because you, on the second, fourth and sixth carbon of this phenol group, you have 3 methyl group attached separately, right? So this is how you normally name any phenol group. So make sure you practice something like this whenever you practice from the textbook, right? So now let's go to the another type of functional group, which we call as a thiol group. And then what are thiol group? Thiol group are the compound that contain an SH group. So basically this is SH. If you remember alcohol, this is your alcohol. The only difference over here, instead of oxygen you have sulfur in thiol, right? And then sometimes this SH group is also called as a sulfhydryl group, a sulfhydryl group. So make sure you remember this terminology too. So if you see this structure over here, you have a benzene ring, benzene on the top of benzene, you have SH group. So this is your thiol group. Again, you have a skeleton line structure, you have SH at the end, this is thiol group. So make sure you don't get confused between alcohol and a thiol, because thiol has an SH in it, and alcohol has an ONH in it, right? So there's a difference between sulfur and oxygen in thiol and alcohol. Now let's try to learn how to name any compound that has a thiol group in it. So the thiol are normally written as alkane thiol, right? For example, how many carbon you have in here? One carbon is methane. But which functional group you have in here? SH group. SH is thiol. So you just write at the end thiol, the ending word. So methane thiol was the name. And you have to give the priority to the carbon that contain the SH group, right? Is the same concept that we done with the alcohol. So this is 1, this is 2. So I can say methane, ethane. So this is ethane thiol. You have 2 carbon. And if the thiol group are not present on the first carbon, then you have to give the location of that thiol group, right? For example, if I have this structure SH, so if you can see in this time the SH group is not present on the first carbon, so you have to start counting from here, because you have to give the lowest location number on the SH group. So 2, 3, 4, 5. 5 is what? Pentane. And then this is thiol, pentane thiol, but you have to specify the location, because this time the thiol group is not present on the first carbon, is present on the second. So 2 pentane thiol. Or you can also write pentane 2 thiol. So both way of writing are right. So if you know how to name an alcoholic molecule, you can name thiol group, right? The only difference is ending word is the thiol. So now let's talk about what are thiols and what's the function of thiol in nature and industry. So the important characteristic of the thiol is they have a strong odor. So if the thiol compound is present nearby, you can smell it easily because of its strong odor. So I think everyone already cut the onions. So onions also have a thiol called propane thiol that cause eyes to water, causes, right? And because of this compound in onions, you will always get watery eye whenever you cut an onions, right? Then the skunk prey also contain a thiol group, right? And then some thiol compound also be added into a natural gas, so that if there is any leak, you can smell it easily. So this is the function of any thiol containing compound because of its strong odor. Now let's try to name these simple thiol. So the time I say this is SH group, I know this is a thiol. You can start from here 1, 2, 3. In this case it doesn't matter, you can also start from 1, 2, 3, because the second carbon getting the thiol group in both the cases. So the name is 3 is propane, and you have a thiol, propane thiol, and you have to just write the location 2 propane thiol. Same thing over here, you have to start counting on this 1, 2, 3, 4, 5, 6, 7. You cannot start counting on the other side, because you will get a higher number to the carbon that has a thiol group. So you have 7 carbon, 7 is heptane, you have a thiol, heptane thiol, and the location of the thiol group in this compound is not on the first, is on the third, 3 heptane thiol. And what about this one? You have to start from here 1, and how many total carbon you have over here? 1, then 3, 4, 5. 5 is pentane thiol, and where do you have the thiol group? On the first carbon. If you don't want to write the 1, you can also just write pentane thiol. So this is how you normally write the naming of these thiol. So now we're going to talk about another functional group which we call as ethers. So ether functional group is an oxygen atom with single bond to 2 carbon atom. So something like this, R, O, R. So I can take an example, CS3, O, CS3. So if you can see one of the R group, second R group, and you have oxygen at the center, right? So if you find this kind of structure, that means we are talking about an ether. So R can be a carbon chain, or it can be a ring, something like this. You have an oxygen. So what you have over here, you have this carbon, you have this carbon, and you have oxygen at the center. So this can act as in a ring, something like this too, with oxygen in here. And this R group can be an aromatic group. So this is a benzene, it react with O, and you have, it can be CH3. So in this case, one of the R group is your aromatic, another R group is simple carbon containing, or an alkyl group, and you have oxygen at the center. So R, O, R. And then what's the molecular geometry of this ether? Bent. Why? Because you have R, O, R, and then you have a non-bonding electron, a pair of electron on the oxygen. If you remember from the shape, when we talk about the VSEPR theory, how you're gonna determine the shape of any molecule, it depends on if you have any lone pair or the non-bonding electron pair on the central atom. So in this case we have, then the structure will be bent because of the presence of these non-bonding electron pair on the central atom, which is oxygen. Right. So let's go to the next slide, and then we'll try some example of an ether. So these are some of the example of the ether, right? You have, this is one of the R group, this is second R group, and you have an oxygen at the center, right? And we can also show a skeleton line structure with 2 carbon on each side on the center oxygen, right? Similarly, we can have one of them can be a benzene, and then another one can be a just carbon containing an alkyl group. And this benzene is an aromatic compound, right? So we can also say ROR. In this R is aromatic, right? And we can also show in a line angle formula or the skeleton line structure, you have a benzene, then you have 1 carbon on this side, right? And you have oxygen at the center. So this is a different way we can see the ether with a different R group. Then the next thing is how we normally name an ether, how you name it. So the naming of ether is sometimes we use as a common name. So common, whenever you write a common name, you have to just see what kind of group you attach across the oxygen atom, and you just write the name of the alkyl group or the R group. So in this case, you have on one side of the alcohol, what you have? Ethyl group. Another side, you also have an ethyl group. So I can say diethyl ether. The ending word will end with ether because we are talking about ether. So you have diethyl ether, 2 ethyl on each side of the oxygen, right? Right. Then if I give you one more example, if we have something like this, then what's the name of this ether? I know this is an ether because you have this R group, you have this R group, and you have an oxygen at the center, right? So this R group is your methyl, this R group is your propyl with 3 carbon, 1 2 3. Then the name you can write alphabetically, so you can write methyl propyl ether, ending word is ether, methyl propyl ether. So this is how you normally name a common name, right? But sometimes for a more complex ether, you have to use a IUPAC name, right? The scientific name. So how you going to write the IUPAC name, we'll try into the next slide. So let's try to do some IUPAC nomenclature for an ether. So let's say if you have this structure again, then you have to just see on which side on across the oxygen, which side has a lesser number of carbon. So this side has just 1 carbon, so we use this lesser number of carbon on the oxygen as a substituent, right? And then instead of writing methyl, we just write methoxy, OXY. So this thing we can act as a methoxy group because one carbon is methane, ending word is oxy, methoxy, and then the parent chain will be the bigger carbon containing chain, 1 2 3 methoxy propane. You just write the parent name, right? Let's take one more example. In this case you have two groups, two carbon on each side, so you can use any of the side as a substituent. Let's take this as a substituent one more time. So you have two carbon is ethoxy, ethane, ethoxy, and then the other carbon you can use as a parent chain, 1 2 1 2 is ethane, ethoxy, ethane. Let's take one more example. If you can see over here, you have oxygen, and across the oxygen you have two R group. So this is one R group and this is second R group, right? So this is a smaller R group with just one carbon, so we can write methoxy, right, as a substituent. And then for this big R group, which is as a parent chain, you have to start counting so that the oxygen atom or the ether or the substituent will get a lowest number, because this OR on the top act as a substituent. That's why we wrote methoxy, right, oxy. So 1 2 3 4 5 6. Then on the third carbon we have a substituent, so you can write 3 methoxy. Then you have 6 is hexane, so 3 methoxy hexane. So the location number telling us that the ether group attached on the third carbon with just methane group attached to that oxygen as a substituent, right, and hexane. So 3 methoxy hexane. Let's take one more example on this. If I have this structure, so over here what we have this one R group and this another R group, right? So this R group has just one carbon, so I can say one carbon is methoxy, and then what's our parent chain? Benzene, methoxybenzene, right? So this is how you write the IOPIC name, the scientific name for any ether containing compound, right? So just practice couple of name, and then you can write both ways, common name, IOPIC name, and we already covered both the name, right? So depending on the problem, whether he's asking just a common name or a IOPIC name, you can just write it down the name. Now let's see how we can differentiate an ether from an alcohol, because if you remember, what is alcohol? The OH group, right? ROH. And what is ether? ROR. So what's the difference? The difference between ether and alcohol is the hydrogen in alcohol that attached to the oxygen get replaced with an R group over here. So sometime it may be confusing that whether we are talking about ether or alcohol. So make sure you know this difference. If the oxygen atom attached on hydrogen on one side and another side with an R, that is an alcohol. If the oxygen attached on both sides with an R group, that is your an ether. R group means carbon. It can be aromatic, it can be alkyl, but it doesn't have any hydrogen directly attached with the oxygen, right? So let's take an example over here. This compound is an ether because this is a carbon from the benzene, this is a carbon from any R group, so you have COC, right? ROR group, so this is an ether. Whereas this compound is an alcohol. Why? Because you have carbon, this is your C, or this entire thing is your R, then you have oxygen, you have the second one as hydrogen, not an R group, so that's why this is an alcohol. And which type of alcohol? A tertiary alcohol, because the carbon that has an OH group has attached to 3 carbon, 1 2 3, so tertiary alcohol. So this is how you can differentiate. Let's go to the next slide and then try to do some more problem based on the same concept that we just learned about the differentiation between alcohol and ether. So the problem says identify each of the following compound as an alcohol, phenol, thiol, or ether. So you have to make sure remember the structure for each and every functional group that we just learned in this slide, on this chapter, on this PowerPoint, right? So let's talk about this one. The time I see this OH and this entire thing become what? R. So ROH, right? So this is an alcohol. For B part, why this is an ether? Because we have C, so COC, right? ROR, carbon, oxygen, carbon, and this oxygen is a part of the ring, right? So this is an ether. So you always have to just check whether you have ROR group or ROH group, right? So this is an ether present in the form of a ring. Then we have C part, we have OH group, and this entire group is your R, so ROH, alcohol, phenol group. The time I see this R group, what's special about this R group? We have benzene ring or aromatic ring, and the aromatic ring attached with an OH, so that's why it's a phenol group. So let me tell you one more time over here. So the time I see OH and benzene, this is your phenol. And then what about this one? You have this R group, an aromatic group, you have this R group which is a methyl group, then you have oxygen, so ROR. So this is an ether again. So make sure you remember the structure of these functional groups, because sometimes it might get confusing because they are almost similar in structure, or so yeah, make sure you practice a little bit about this so that you don't get any confusion during the problems. Then we have our last functional group, which we call as amines, and then we're gonna talk about the chemical reactivity as a base, how amines can act as a base, right? So before we go to the amine, we already know what the structure of ammonia, which is NH3. We know the structure is NH with a lone pair or a non-bonding electron pair on the top of the nitrogen. So amine is nothing, it's just ammonia where the hydrogen are replaced by the R group. So in this ammonia, if I remove one of the hydrogen and replace with an R group, so this is an amine. I can replace the second H as an R group too, third also as an R group. So if you have any one R group attached with the nitrogen in ammonia, we call that as an amine. And this R group can be a carbon chain, can be ring, can be any aromatic ring. And what's the structure of nitrogen in amine? Is trigonal pyramidal, right? So remember this thing, in amine we have a trigonal pyramidal shape of the amine, right? So there are a couple of examples of the amine. If you can see, this is your ammonia structure. If I remove one of the hydrogen on this with a CS3, if you see over here with an R group, this is your amine, CS3NH2. If I remove the second hydrogen again with any R group, in this case is CS3 again, then you have CS3 NHCS3. I can also remove the third one and replace with one more CS3 group, then you have CS3N, CS3, CS3, and this is the skeleton line structure, right? You have a nitrogen, out of the 3 bond, one of the bond is an alkyl group and the other 2 you have to show the hydrogen, right? Because you just don't show the hydrogen on the carbon, but you also always show hydrogen for any heteroatom. Same thing on the over here. Out of the 3, 2 are now replaced with an R group. Then the third one is over here, right? And then if you have any amine, if we replace one of the hydrogen with an aromatic ring, which is a benzene, then we have a special name for that particular compound, like aniline. Like we have a phenol where benzene ring attached with an OH group. If you remember from the phenol, from the alcohol, this is your phenol, right? Similarly, if you have a benzene attached with an NH2, then we have aniline. So this is a parent name again, like we have phenol. So make sure you remember this kind of thing too. Now let's talk about what are the different types of amine we have, right? Like we have different types of alcohol, we also have a different types of amine, and this is also the same: primary amine, secondary amine, tertiary amine. Same like an alcohol, primary, secondary, tertiary alcohol. So what are primary amine? So this is your ammonia, NH, H, H. This is your ammonia. If one of the hydrogen replaced by any R group, that's your primary amine. If you replace 2 hydrogen with an R group, secondary amine. If you replace all the 3 hydrogen with all the 3 R group, tertiary amine, right? So primary amine is 1 group, 2 hydrogen atom. Secondary 2 R group, 1 hydrogen atom. Tertiary 3 R group and no hydrogen atom. So these are the example: 1 R group, 2 R group, and all the 3 bond replaced by R group, tertiary amine. So if you have any structure, you have to just see how many R group attached to the central nitrogen. You can easily figure it out what kind of amine is that one, primary, secondary, or a tertiary amine. Now let's try to learn how to name a name of the amine, which is a common name. So we're not gonna use an IOPIC name for amine, we are just going to learn the common name. So how you normally name an amine, you have to just write the name of the alkyl group that is attached with the nitrogen, and then ending word should be end with amine because you're talking about amine. So you have one R group in the form of methylamine. Now you have 2 R group and both of them are methyl. So you have 2 methyl group, dimethylamine. Then you have 3 trimethylamine. If you would have something like this, then what's the name? This is ethyl, this is ethyl, this is also ethyl. So the name will be triethylamine. You have 3 ethyl group. If I would have something like this, and let me remove this one over here. If I have something like this, so you can write the same name as you have methyl group, you have methyl group, you have ethyl group in here. So what's the name? You have to go alphabetically. So you can write dimethyl ethyl amine, because you have 2 methyl group, 1 ethyl group. So the name is dimethyl ethyl amine. Let me write over here. Let me go all the way up so you can see the name. So you can say dimethyl ethyl amine for this structure. So this is how you normally name it. And if I ask you which kind of amine is this one, this is your primary amine. This is your secondary amine because you have 2 carbon attached to it, 2 R group attached to it. This is your tertiary amine because you have 3 R group attached to the nitrogen. Right, so this is how you can verify which kind of amine you have along with the name. So now let's talk about the physical property of the amine, right? So if you can see from the structure, let me draw the structure for primary amine. This is N, this is R, this is H. This is your primary amine. This is your secondary amine where 2 are 1H, and tertiary amine is all the 3 are R group, right? So if I ask you, out of the 3 types of amine, primary, secondary and tertiary amine, which kind of amine can form a hydrogen bond? So to make a hydrogen bond between themselves, amine has to have any hydrogen attached with the nitrogen, right? This is a requirement. So in primary and secondary amine, you have a nitrogen directly attached with the hydrogen, and then if you have any nitrogen, oxygen or fluorine come nearby it, they can make a hydrogen bond, right? Both of them. But for the tertiary amine over here, you don't have any hydrogen attached with the nitrogen directly, so the tertiary amine cannot form a hydrogen bond. And if they cannot form a hydrogen bond with themselves, they will have a lower boiling point compared to the primary and secondary amine, because they don't have any hydrogen to make a hydrogen bond between themselves, right? For example, this is your primary amine, this is your primary amine. They can form a hydrogen bond over here, right? So if they form hydrogen bond, they will have a higher boiling point and solubility. They can also have a hydrogen bond with water too. If you have any water, they can make hydrogen bond. So primary, secondary amine are also soluble in water, as well as the tertiary amine. What do you think about the tertiary amine? Can they make up the hydrogen bond with the water? Yes, they can make, because if we have any, let's talk about over here, R and R, this is your tertiary amine. If I put some water nearby it, they can make a hydrogen bond. So just remember this thing: the primary and secondary amine can form a hydrogen bond between themselves, whereas the tertiary amine cannot. But all the 3 kind of amine can form a hydrogen bond with water, so they are all soluble in water. Now let's try to do some problem over here. The amine listed below are structural isomer, and we already talk about what are structural isomer. Same molecular formula but different structural formula, or structural different structure, you can say. Write a skeleton line structure for each. So if you have this as condensed formula, you can write the skeleton line formula. Yes, we have nitrogen, and how many methyl group? You have CS3 3 times, so CS3 CS3 CS3. So this is your line angle formula, or the skeleton line. What about this one? If you can see, you have NH. Out of the 3, 2 of them replaced by R, and one of the hydrogen is still attached with the nitrogen. So we can say on one side you have methyl group, another side you have ethyl group, and the third bond still has an hydrogen. And the last one, you have nitrogen. Then out of the 3 bond, only one of the bond has an R group, which is over here. So this is your R group, and other 2 bonds are still with hydrogen. So this is your primary amine, this is your secondary amine, this is your tertiary amine. And predict which amine has the lowest boiling point and why. So which one will have the lowest boiling point? The tertiary amine will have the lowest boiling point, because they cannot form a hydrogen bond between themselves, because it doesn't have any hydrogen. All the bonds are replaced by R. So this is how you can. So only kind of force of interaction they have just dipole force of interaction, which is weaker than the hydrogen bond that the other 2 amine can form between themselves. Now I'm going to talk about an alkaloid, a chemical compound we name as alkaloid. This is nothing, this is just an amine derived from the plant. So amine that is derived from the plant we name as a special way called alkaloids, and it all include morphine and their derivative, right? Like nicotine. If you see over here, you have an amine group. Which kind of amine? Tertiary amine. Why? Because the nitrogen has carbon, carbon and carbon. Then we have some other compound alkaloid too. Now we're going to talk about that amine can act as a weak organic basis, right? And we already learned about water, acid and base from the previous chapters. So water base are those compounds that can accept hydrogen, and then the acid are which can donate hydrogen. So we are already saying amine is a weak base. That means amine can accept hydrogen from some other compound. So amine can react with water as ammonia does by accepting a proton and producing hydroxide ion. So let's go to the next slide and we'll see why amine act as a base when it react with water. So if you remember that when we did the ammonia example with water, this is your ammonia. Ammonia has a lone pair, and water can act as an acid. Ammonia can take this hydrogen, right, and convert into ammonium ion, right, because the lone pair is being shared entirely by nitrogen, right? So they will get a positive charge, and then rest of the thing is hydroxide ion, right? So that's why ammonia is a base, water is an acid, then ammonium ion is your conjugate acid. Now it has one extra hydrogen, that's why it's an acid, conjugate acid, and OH negative is your conjugate base. Same type of reaction is shown by the amine. And if you see an example, this is your methylamine. You have a methyl group, CH3 group, and then you have NH2, right? When it react with water, nitrogen still have a lone pair on the top of it, and the hydrogen will go and attach to this lone pair, right? And then the time it attach, nitrogen will get a positive charge and oxygen will get a negative charge. So you will get a conjugate acid during this reaction, and then a hydroxide ion as a conjugate base. And because of this reaction with water, amine can act as a weak base. And if you can see why this is a weak base, because most of the time reaction is going backward. If you can see the arrow, we have a bigger arrow going backward compared to the forward arrow. So that means the reaction is mostly going on the backward towards the reactant side compared to a product side. So it's not a strong base because it doesn't allow the reaction to go towards the product side, right? So it's a weak base. We can take one more example. When ammonia react with an acid, what's the reaction? The reaction is still the same. Then hydrogen go and attach with the nitrogen because of the lone pair. It will get NH4 plus, and then Cl will get negative, right? So ammonia convert into a conjugate acid, and chlorine, hydrochloric acid, chlorine converted into a chloride ion, which is a conjugate base, and they always stay together, is in the form of a salt, right? And if you remember from the previous chapter, whenever the base react with an acid, it will always form a salt plus water, right? So you will always form a salt. And then what's special about this salt? Now you have the charge plus and negative, right? So that means amine salt are more soluble in water compared to the just ammonia, right? Because ammonia is, right? Then we'll do the same reaction with an amine like we did for the ammonia. Let's go to the next slide and try to learn the reaction with an amine. So now we're gonna do the same reaction that we did with ammonia and hydrochloric acid. We're gonna use one amine. If you can see this entire structure, you have an alcohol, you have an amine over here. And which kind of amine you have? You have secondary amine over here, right? So when it react with hydrochloric acid, this lone pair nitrogen accept the hydrogen and convert into one hydrogen convert into a positive charge, and the chloride become Cl negative, right, from the hydrochloric acid. And this entire act as a salt because you are reacting base with an acid. right? And then we already talk about this thing, salt has a plus and negative charge, so they are polar. And amine salt are more soluble in water than their neutral amine, and because of this characteristic they are preferred form of use for pharmaceutical sciences, because they can easily be dissolved in water and you can make a solution. Now let's take an example. Write the product of the following neutralization reaction, then label the amine acid and amine salt. So you have this structure. The time I say this is an amine. Which kind of amine you have? This is a secondary amine. You have this R group, you have this R group. Then this is an acid. Because why I know this is an acid? Because after the reaction the hydrogen went over there on this nitrogen, if you can see over here. So this molecule is accepting the hydrogen coming from this molecule. So in this case this is an acid because donating the hydrogen. This is act as a base, and this one act as a salt, right? You have a positive and negative, right? And then this is a neutralization reaction. Acid plus base form a salt. So now this is just an overview of all the functional group that we talk about in this chapter on this slide, and make sure you know how to differentiate between each of them, right? Whenever you see any functional group you have to know that which functional group we are talking about. So if you see something like this, OH, I know is an alcohol, and which type of alcohol? Primary, secondary or tertiary alcohol. Similarly you should be able to differentiate between the other three type of functional group in hydrocarbon, alkene, alkyne and aromatic. Then we talk about the phenol group, then thiol group, then ether, ROR. And then for the amine, make sure you also differentiate between primary, secondary and tertiary amine, and how you, if I give you any compound, you should be able to understand which kind of amine is that one, right? So I think that should be it from this chapter or this video. And make sure you just see the video, check your PowerPoint, as well as read from the textbook, right? That will cover everything. Then I'll see you in the next video then. Bye.